So for 12.6, we're going to be solving exponential and logarithmic equations. And we're going to start off with a pretty basic idea. If I have a to the x is equal to a to the b, if I have the bases that are equal, then basically I know that these will equal if the bases and the exponents are equal. So if the bases are already equal, then we can just set the exponent, x, equal to b. If the bases are equal, we can set the exponents equal. Here's an easy example of that. If I have 2 to the x is equal to 2 to the third, 2 to what power equals 2 to the third? If the bases are equal, x must equal 3. Okay? So when we go on now, and I keep looking at some more examples of this, I've got 2 to the x equals 8. See, and you're like, well, yeah, but the bases aren't equal. But we can make them equal, right? We can write 8 as base 2. See, 2 to the x is already base 2, and 8 can be written as 2 to the third power. Not 2 to the fourth power, 2 to the third power would be 2 times 2 times 2, or 8. Okay? So when I have these bases equal now, when I make these the same base, I can just set the exponents equal. If I got 2 to the x plus 1 is equal to 32, 32 is also base 2. 2 to the fourth would be 16. 2 to the fifth would be 32. So what I do is I rewrite that 32 as the same base, so that I have 2 to the x plus 1 is equal to 2 to the fifth. So now I can set the exponents equal and get that x plus 1 is equal to 5. Subtracting the 1, I get that x equals 4. And that'd be pretty easy to plug in. I would end up with 2 to the fifth equals 32. This is more of an introduction. We're going to kick it up a bit right here. So now I've got 9 to the x plus 1 is equal to 27. You're like, well, wait a second, 9 and 27 are not the same base. And I know that 9 to the first is 9, 9 squared is 81. So I'm not getting a 27 from a 9, right? But this time I've got both the 9 and the 27, and they're both the same base. They're both potentially base 3. 9 is 3 squared. 27 is 3 to the third. So what I can do is I can rewrite each of these. The first one is now 2 squared raised to the x plus 1 is equal to 2 to the third. On the left side, you have to catch our exponent rules that we discussed in the last section. When I have a power to a power, this basically becomes 2x plus 2. The 2 distributes, they multiply together. So just like we had before, if I have b to the x to the y is equal to b to the x times y, basically that 2 is going to multiply across that other group. So now that these bases are equal, I literally could just set the exponents, 2x plus 2 equal to the 3. Because again, I distributed that 2, so I multiplied those two together. So now when I solve, I subtract the 2 and get that 2x is equal to 1. Dividing, I get that x is equal to 1/2. Wrong button. So now I have 4 to the x minus 1 is equal to 1/8. And once again, I look at the 4 and the 8 and I go, man, I could write those both as the same base, right? 4 is written as base 2. 4 is the same thing as 2 squared to the x minus 1. Remember that those are going to multiply to give me my 2x minus 2. The 1/8 you got to be a little trickier with, because I know that 8 is 2 to the third, but to make it 1 over, to flip it down, I need that exponent to be negative. 2 to the negative third would make it 1 over the 8. Okay? So now that these bases are equal, I can set the exponents equal. Multiplying these again gives me 2x minus 2 is now equal to, how about negative 3? Adding the 2. 2x equals negative 1/2. Negative 1, sorry, jumped ahead there. And then dividing by the 2, x is negative 1/2. Alright, onward. Now I got 2 to the x equals 5. See, this one's different, because I'm looking at this going, well, I see the 2 and I see the 5, and 5 is not written as base 2. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. They're not making each other, and I can't rewrite base 2 as another base. So what do? Well, you have to catch the fact that what's happening to x here is x is an exponent. Sometimes I'll say it's being exponented, right? X is an exponent. I say it's being exponented, right? So what's the inverse of that? And I'm not going to do, remember the xth root, that's not going to do us any good. It's not going to help me solve for x. I can't do that. I'm not going to do like a second or third root or an xth root. What we have to do is we have to have another inverse for when x is an exponent, and we have that, and that is where we log both sides. Why? Because when I log both sides, that exponent can be undone. Using our rules of expansion, an exponent can now turn into multiplication. What does that do for me? Well, now that x isn't the exponent, now that x is just being multiplied by log 2, to undo multiplication, we divide, and we end up with x is equal to log 5 over log 2. That would be our exact answer. Or approximately, and we did this in the last section, so there shouldn't be an issue, that we should be able to write log 5 divided by log 2. So that would be log of 5 divided by log of 2. And 2.32193. 2.32193. And we could actually check that. See, our original question said 2 to what power made 5? And prior to this chapter, we're like, I don't know. I know it's somewhere between 2 and 3, but that is not a number I want to deal with, right? But we could actually check that 2 raised to the 2.32193 should equal 5. In fact, if I leave it on the calculator and just do 2 raised to that previous answer, 2 raised to that previous answer, it's going to go, yeah, 2 to that power is 5, no problem. I think that's pretty cool. There is another option. This is probably my least favorite, but you could hypothetically take that 2 to the x is equal to 5. And if you're going into the statistics approach, you're not going to be doing a lot with logarithms past this course. There are some cool things in statistics with logarithms, but it's not in our intro to stats, so don't stress out about it. But you could rewrite this in logarithmic form. So we've done this before. Log base, well, what's the base of the result is equal to the exponent. And what would that do for me? Well, I could use the change base formula now and do log of 5 divided by log of 2, and I end up with that same answer. That's a great trick. I would encourage you, especially those of you who are going into the pre-calculus direction, you need to be able to handle this algebra. Let's keep going. Once again, I can't write 3 as a power to make 4. There's no pretty number for that. So what do we have to do to solve this? Is we log. X is being exponented. It's being multiplied by 5. So we're going to log it so that that exponent can now move to the front. So what do we have here? 5x log 3 equals log 4. Okay. Now x is now no longer an exponent. It really is just being multiplied by two things, both the 5 and the log 3. So if I want to just get rid of both of those, I can make my life a lot easier by just dividing both sides by 5 log 3, 5 log 3. What do we end up with? X is equal to log of 4 divided by 5 log of 3. This is what we would call our exact solution. And there are some in the homework, and there's going to be some on the test where you can expect me to ask you for an exact solution. And I would expect the answer to be left like this. How would I get the approximate solution? Or it will be as a decimal as our approximate. Okay. So if I want the decimal, then we're going to do log 4 divided by 5 log 3. So that would be log of 4 divided by, and you'd have to group the 5 and the log 3. Okay, so this would be what a lot of you have to do depending on your calculator. You got to make sure you group that bottom so you're not just dividing by 5, but you're dividing by the entire group so that we get the 0.252372. There is another option. For those of you who have a little fancier calculator, you can actually do the log of 4. And especially, I know on the updates on the 83s and 84s, it'll have this feature that if you hit Control Divide, it'll actually create that fraction. So I don't have to worry about grouping. I just put the 5 log of 3 on the bottom, and then it automatically has them grouped. Makes that a little easier. So just some options there. That Control Divide is a nice clean way of creating a fraction where you can fill in the top and bottom and not have to worry about some of the old grouping issues. So 252372, 252372, 252372. Now obviously in your homework they have you round that to probably 2524, or whatever. They're going to have you round that. So I'm assuming you know how to do that by now. This is a special one. You're like, I don't see what's so special about this. Okay, well let's start dealing with it and let's see what happens. So x is still being exponented, so I'm going to still log both sides. This whole group now moves to the front. But what happens here is I have log of 10, and here's where those of you who really understand your logs know that this is something special. Because when I don't have a base, this is log base 10, and we know that log base b of b is equal to 1. When the base and the result are the same, the exponent must be 1. So this is basically canceled out. It becomes a 1. So that's kind of special, is when I can use a log with the base that's the same, they literally can just cancel each other out and leave me with the 3x minus 1 equals log of 4. Which means now I can just add the 1 and divide everything by 3. So that x is equal to, what is that, log of 4 plus 1 all over 3. That would be our exact solution again. So if I asked for an exact solution, that's what you type in. If I wanted an approximate solution or a decimal, log of 4 plus 1 divided by 3. I'm going to use my fancy trick, Control Divide. Log of 4 plus 1, not 11, divided by 3. And let me double check that. 4 plus 1 divided by 3. 4 plus 1 divided by 3. So how about 0.53402? 0.53402. That would be our approximate solution. Okay. So that's kind of the big part. We're going to do a couple more with solving, but here's another one that kind of, if you don't recognize yet that this one's special, probably, but if you didn't, that's okay. Unfortunately, you would log both sides, and there's nothing wrong with this. It would help the t would now move to the front, so I would have t times log of e is equal to log of 5, and then I would just divide both sides by log of e, and you could have an exact solution that way. But there's an easier way. See, we were able to undo the base 10 last time really easily because we had a log base 10, right? Well, here I have e to the t is equal to 5. If there were only some way of doing a log base e. Well, there is. It's even in your calculator, right? Log base e is the natural log. So you can make your whole question a lot easier if you go, oh, if there's an e, rather than log both sides, let's use natural log, which is log base e. The t still moves to the front, but what is the natural log of e? What is log base e of e? Right? So I just get t is equal to the natural log of 5. I think that's a little easier. Does it change the answer? No. I'll show you. Let's do the natural log of 5, which I think was the easier of the two answers. And here's what the rest of you have to do if you don't see that. You would do log of 5 divided by, and then you would do log of e, and then you'd have to go, oh man, I just put that in the wrong spot. Go over here, put the e there. Wrong button. Messy, messy, messy. There we go. E, but I got to give it an exponent, so you'd have to do log of 5 divided by log of e to the first. And I get the same answer. But that's a little harder than just going, oh, if it's an e, why not use log base e? Why not use the natural log? 1.60944, 1.60944. And once again, this I could actually check. Go back and I could say, look, e to the should equal 5. I can check this, the original question. And I think that's where this gets kind of cool, is that I can actually say e to the answer equals 5. All right. Here's another question that if you see, there's actually an easier way to do this, but if you don't, I'm going to have a lot of people look at this and go, oh man, you know, 4 and 1/8, I don't know, I'm just going to log both sides. And then the x minus 1 comes to the front, so now I have x minus 1 times log of 4 is equal to log of 1/8. Ugh. And then I would undo the multiplying by dividing. So now I have x minus 1 is equal to log of 1/8 divided by log of 4. And then we would add 1 at the end, and this would be our answer. But what is log of 1/8 divided by log of 4 plus 1? Well, let's see. Log of 1/8 divided by log of 4 plus 1, negative 0.5. Negative 0.5. So x is just negative 0.5. Interesting. Haven't we done this before? See, this is a question that if you don't see the easier way, you can go through and use logarithms, and I will have a lot of people when you get to the test not see the easier way, and so they'll use logarithms, they'll get to this answer, they'll type it in, and it'll be right. But the easier way was to see that the 4 and the 8 both shared a common base, and we've already solved this back at, I think, example, I don't know, something earlier, and we end up with 2x minus 2 equals negative 3, 2x is equal to negative 1, so that x equals negative 1/2. See, it's easier if you can make them the same base, but if you don't, it doesn't mean your world ends, it just means you're going to be dealing with a much harder question than it needs to be, but you still get the same answer. So that's going to be basically solving when x is an exponent. Our last little bit is, what do I do when x is inside the logarithm? Well, there's an easy way, and there's a trick to this, but I want to just make sure we get through the algebra and make sure we actually understand what we're doing as well, because we just said the inverse of x being an exponent is a log. So what's the inverse of a log? It is an exponent. Now, it's not like raising both sides to an exponent. That was what we would do if we had a second or third root or fifth root. What we do is we actually raise both sides as an exponent to the same base. What base? Well, they already told us. This is base 3, so we raise it both as the power of 3. Right here, b raised to the log base b of x. These cancel, leaving me with the x. They are inverses of each other. So when I do this, the 3 raised to the log base 3 are inverses, leaving me with x is equal to 3 to the 4th, or leaving me with x is equal to 81. You're like, that is crazy. Well, let's start with this. I think this is one of the coolest applications of whatever I do to one side, I can do to the other. I literally can raise both sides of the equation as an exponent, not to an exponent. I can make them both an exponent of the same base, and it stays true. If you don't like this, or if you're not one of my students going into pre-calculus, then you could kind of use a trick with this and go base to the exponent equals result. You literally could just go base 3 to the exponent 4 is equal to x. You won't always be able to do that, but on some easy ones, feel free to just rewrite them. But I would encourage you to know the algebra. We are undoing the logarithm with a base raised to that exponent. Okay, so it's kind of a weird application. Probably the weirdest one that we do, but it's also, I think, one of the coolest. Here. Yes, I could just rewrite it, but what is the base? How do I undo log base nothing, right? Well, you have to remember that is log base 10. How do I undo log base 10? Well, I raise both sides, not to the 10th power. No, right? That's if we had a 10th root. We raise both sides as an exponent to base 10. Because 10 to the log base 10 cancels, leaving me with 2x is equal to 10 to the third, or 1,000. Okay? If you don't like that, you could rewrite that as 10 to the third equals 2x. Gets you the same direction. I like the algebra behind it. But last but not least, we divide both sides by and get that x is equal to, looks like 500 this time. Onward. What do I do when I have logs on both sides? Well, both of these are basically what? Log base e. So when I raise them as an exponent, I'm going to just raise them as an exponent of base e. Because if, what did we say? B to the log base b of x cancels and leaves us with just x. So basically e to the log base e, or to the natural log of x, equals x. These cancel each other out. They are inverses, leaving us with 2x equals 8. Welcome back to introductory algebra, right? Within one step, one scary step, but at that point, you just divide by the 2 and get that x is 4. And check that, guys. It's not that scary. If I plug in a 4, I get the natural log of 8 is equal to the natural log of 8. Doesn't that make sense? I know it's profound. 2 more. What do I do when there's a couple logarithms and they're not just like on both sides, there's like 2 logarithms? It's like, well, when there's one log, it's easy. We just undo it. I have people that have done this before, 10 to the, and then they've got this subtraction problem in the exponents, which is complicated. Mathematically, we could approach it, but there is an easier way. See, if they're not one log, or if it's not just a log on each side, then basically we try to make everything one log. How do we make it one log? Condense. So we're going to use the skill from the previous section. I can bring these 2 logs together as a single log, and subtraction turns into division. So what can I do now? I can undo the log. This is log base 10, so we raise both sides as an exponent of. The left side cancels out, leaving us with x over x plus 3. Right side, 10 to the negative 1 is 1/10. How do we solve this? We haven't seen this for a while, but it shouldn't be too hard. We cross multiply. So I have 10 times x, or 10x, is equal to x plus 3. Isolate the x. 9x is equal to 3. Divide by the, and get that x is equal to friggin' 1/3 at the end. Whew. They get trickier, right? This is obviously a trickier one, but the idea is that if there's multiple logarithms and they're separated by adding and subtracting, not a big deal. Bring them together. Use your rules of logarithms. Condense them together. But beware. See, log of x, x can't equal 0. Remember, there's a restriction on logarithms. Whatever's in there can't equal 0 and must be greater than 0. It must be positive, right? So when we look at this last example, Apparently I'm going to look at the previous example first. When we look at this last example, once again I have two logs and they are being added. So we can condense them together and addition turns into multiplication. I end up with x minus 9 times x, or x squared minus 9x. They multiply together. Subtracting turned into division, addition turns into multiplying. So log of x squared minus 9x now equals 1. Most common mistake that people do is they'll just make x squared minus 9x equals 1. That log doesn't disappear. These just condense into a single log. So you still have to undo the log. How do we undo the log? Same way we did last time. How do I undo log base 10? For the last time, I hope you get it by now, we raise both sides as an exponent of base 10. So that I have x squared minus 9x is equal to, not 1 to the 10th, 10 to the first. Totally different. So please be careful with that. How do I solve this? We've solved these before. X squared plus bx plus c, get it set equal to. How do we solve this? There's an F word for that. We're going to F this. We're going to factor, right? We've done this before. What multiplies to make 10 combines to make 9. To make a negative 9. So that x is equal to. Whew. One scary word. See, there are restrictions on logarithms. So you have to go back. And not a big deal. I mean, you don't have to go back, and you could plug in the numbers if you want to. But just think logically. Are there either of these numbers that when I plug in make a negative or a 0 in the logarithm? Well, let's start with the 10. If I plug in a 10, 10 minus 9, I end up with log of 1 plus log of 10 equals 1. Those are both positive. I don't even have to type that in. That one's okay. What was our next one? A negative. Hopefully the negative's already making you scared. Negative 1. That would be log of negative 10 plus log of negative 1. We got a problem because what's inside the logarithm cannot be negative. It must be positive. So that means that this answer is extraneous. And so our only answer is really x equals 10. So please be careful with that. Those rules for logarithms don't just disappear. They're kind of tricky, but that should be it for 12.6. So if you're not going for the extra credit, you're done with Chapter 12. We'll do a little bit with 13 and 14, and then you're ready for the next test and the final. Keep it up.